In this lecture, we are going to discuss the Faraday law of electromagnetic induction. It was Michael Faraday who in 1831 discovered the phenomenon of electromagnetic induction. Electromagnetic induction is a phenomenon in which an induced EMF is produced. Induced electromotive force is produced in conductor whenever there is a change in magnetic field. Magnetic field. If I simply explained electromagnetic induction is a process whenever there is a change in magnetic field near the conductor, then there will be a production of an electromotive force in conductor. So as we know that, dear student, magnet has two poles. One pole of the magnet is known as north pole and second pole of the magnet is known as south pole. Magnetic field of lines are generated from the north pole of the magnet and they go toward the south pole of the magnet like this. Whereas the magnetic field of lines in south pole are directed inward toward the south pole like this. So whenever this magnet is moved along either in forward direction with a certain velocity or in a backward direction or in opposite direction with a certain velocity, there will be a change in magnetic field. And suppose that if we have a conducting coil, suppose we name this coil as C. If this conducting coil is placed near the magnet and this magnet goes toward or away from this conducting coil, then the change in magnetic field d del B will basically produce electromotive force. So this is basically called a magnetic induction, and a production of an electromotive force due to change in magnetic field is known as electromotive force. The law on the basis of production of electromotive force due to change in magnetic field, Faraday proposed two laws of electromagnetic inductions. These laws were transferred into a mathematical form by a scientist known as James Clerk Maxwell. And equations proposed by James Clerk Maxwell are known as Maxwell equations. So now, the student, before discussing the Faraday law of electromagnetic inductions, we need to understand what type of experiments Faraday proposed. What type of experiment Faraday performed. And on the basis of Faraday experiments, Faraday proposed Faraday's laws of electromagnetic induction. Michael Faraday, let us discuss about the Faraday experiment. Faraday used a magnet having a magnetic field of lines directed inward like this. And in his first experiment, Faraday used a magnet having a uniform magnetic field. Uniform magnetic field B. And the magnetic field of lines of this magnet are directed inward. The symbol cross basically indicate the inward direction of magnetic field of lines. Faraday placed a conducting coil inside the magnetic field of lines, and he observed that if the magnetic field of lines do not change, or the magnet is basically have a uniform magnetic field, then in this case the conducting coil do not attain an induced electromotive force. So the electromotive force in this situation for a coil was zero, and the current for the coil was also zero. However, Faraday observed that whenever there is a change in strength of magnetic field of line, suppose that X, the size of X represents a change in magnitude of magnetic field of lines. And this change of magnetic field of line take place in different amount of time. Suppose this is a schematic representation of a conducting coil. So the magnetic field is non-uniform. So Faraday observed that whenever the magnetic field of lines are non-uniform, then there is a change in magnetic field strength at distance at instant in a particular instant or particular instant amount of time. Let us discuss about the Faraday experiment. Faraday experiment, on the basis of which Faraday proposed Faraday law of electromagnetic induction. Dear students, Faraday used in first experimental setup, Faraday used a uniform magnetic field. And in this uniform magnetic field was directed inward. The symbol X represents the inward direction of magnetic field, inward B. So Faraday incorporated a magnet and a conducting coil inside the inward magnetic field. And since the field is uniform, Faraday observed that whenever the conducting coil is placed in a uniform magnetic field, there is no change in induced electromotive force, or there is no production of electromotive force, and hence the current in a coil will be zero. Now, here was interesting part to come. Faraday again used a magnet having a different magnetic field strength, or having a magnetic field of line having different strength. The cross, basically the size of the cross represent a variation or change in a magnetic field, a magnitude. So he observed that whenever the conducting coil is placed, sorry, let me color it. Whenever a conducting coil, suppose this is a conducting coil, whenever a conducting coil is placed in a variable magnetic field, variable magnetic field, or magnetic field which is different in at different positions. So whenever a conducting coil is placed in a variable magnetic field, there will be a production of electromotive force. And whenever there is an electromotive force in a coil, then there will be a production of induced current. So in such situation, whenever there is a variable magnetic field, there will be electromotive force, and there will be a generation of electric current, induced electric current in a coil. So induced current. So this means that a variable or changing magnetic field B basically produces in EMF, and EMF is associated with induced current. So induced current will be produced in any conducting coil whenever there is a change in magnetic field of line, or there is a change in magnetic field strength near the conducting coil. In third Faraday experimental setup, Faraday used a constant magnetic field like this. And this constant magnetic field was directed inward, uniform magnetic field. The direction of the uniform magnetic field was inward. And whenever he placed a conducting coil C inside the magnetic field line, or inside the magnet having a magnetic field of line directed inward, Faraday observed that if this conducting coil changes the shape, the shape changes, he observed that there is a generation of electromotive force in that wire. If this wire expands like this, or it contracts, then continuously at a particular instant of time, then there is a generation of electromotive force due to change in a size of due to change in the shape of a wire. And whenever there is a generation of electromotive force, there will be a production, or there will be an induction of a current in a wire. So current will be induced whenever there is a change in a shape of wire, or whenever there is a continuous change in a shape of wire. Please keep in mind that continuous change in a shape of wire inside the constant magnetic field is very important, because the continuous change, since you know that a magnetic flux phi B is equal to BA cos of theta. So A is basically is a representation of an area vector. A is area vector. A is area vector. A is area vector. So whenever, and this area vector is basically, it is perpendicular it is perpendicular to the surface of a coil. So whenever there is a change in area vector, there will be a generation, or there will be a change in magnetic flux or magnetic field of line. So the change in magnetic field of line will basically cause a generation of electromotive force. So these were the three main experimental setup which were performed by Michael Faraday, and on the basis of these three experimental setup, Faraday proposes his law of electromagnetic inductions. So let us conclude the Faraday law of electromagnetic induction of the Faraday experimental setup for the proposition of Faraday law of electromagnetic induction. Faraday, in first experiment, Faraday used a uniform magnetic field, and in this uniform magnetic field, in third experimental setup, Faraday used a uniform magnetic field. And in this uniform magnetic field, uniform magnetic field, he incorporated a conducting coil whose shape or whose size or shape, size and shape changes in shorter amount of time. So Faraday observed that whenever there is a change in a shape, suppose that the wire shape size basically increases, he observed that whenever there is a change in a shape in a uniform magnetic field, a change in a wire, a change in a shape of a conducting wire continuously in a uniform magnetic field, there will be a generation of an electromotive force, and this electromotive force will result into a production of an induced current inside the conducting wire. So this means that the reason for generation of electromotive force in a conducting wire is quite simple. Since you know that a magnetic flux phi b is equal to b into a cos of theta. A is area vector, and this area vector is always perpendicular to the surface of a material. So it will be directed perpendicular to the surface of a material. So whenever the shape of the conducting wire changes, this means that the area vector is basically changing. So the change in area vector will basically cause a change in a magnetic flux. And the change in a magnetic flux will basically result into generation of an electromotive force. An electromotive force will basically cause a production of an induced current in a wire. So these were three basic experimental setup. On the basis of these experimental setup, Faraday proposed his laws of electromagnetic inductions. So now, dear student, let us discuss Faraday laws of electromagnetic induction. Now let us discuss Faraday first law of electromagnetic induction. first law of EMI, or electromagnetic induction. Faraday's first law of electromagnetic induction states that whenever there is a change in magnetic flux, whenever there is a change in magnetic flux, linked with conductor, linked with conductor, then there will be production of electromotive force in a conductor, and if the conductor is closed coil, then current will be current will be will also be produced. So now this is very important statement. For electromotive force, or for induced electromotive force in a conductor, it is important to have a change in a magnetic flux. Whenever there is a change in a magnetic flux near a conducting coil or near a conductor, there will be a production of an electromotive force in a conductor. However, in order to get a current in a conductor, it is very important that we have a conductor which is in a form of a closed loop, or which is in a form of a closed circuit. In case if conductor is an open circuit, then there will be a no flow of a current in conductor. However, there will be a generation of an electromotive force. Suppose that, let me explain Faraday's first law of electromagnetic induction with a diagram. Since you know that a magnet has two poles, one pole of the magnet is known as north pole and second pole is south pole. Magnetic field of lines are directed from north pole and they go toward the south pole like this. And the direction of magnetic field are basically lines are inward toward the south pole like this. So now if we have an open conductor, or we have a conductor without any kind of contact or electrical contact, like it is just placed like this. So if the this magnet move in a forward direction, in this direction with a certain velocity v, or in this direction with a certain velocity v, then there will be a production. Since you know that there will be a change in magnetic flux because the magnet basically move in with a certain type of velocity. So the change in magnetic flux means there will be a change in magnetic field of lines. So the change in magnetic field of line will basically result into an induced EMF in this open circuit wire. So EMF will be induced in this wire. However, the current in this wire will be zero because current requires a path. So there is no path in this open wire. Due to this, the current will be zero. However, the induced EMF will be produced in an open circuit wire. So in order to get a current, induced current in a wire, we need a closed circuit. Suppose that we have a closed loop coil. Suppose this is a schematic representation of a closed loop coil. This coil is basically connected with an electrical contact or a device which is very sensitive to the electric current known as a galvanometer. This one is an electrical contact with a device known as galvanometer. So now, since this is a conducting wire, conducting loop, see, suppose that we have a magnet which is placed near this conducting wire like this magnet. And as I have previously discussed, magnet have two types of pole, north pole and south pole. Magnetic field of lines are basically generated from north pole and they go toward the south pole. And magnetic field of line come toward these. So now, whenever this magnetic whenever this magnet come close toward the conducting coil with a certain velocity v, or whenever this magnet go away from this conducting coil with a velocity, with a certain kind of specific velocity v, then there will be a change in magnetic field of lines. There will be a change in magnetic field of line, and this change in magnetic field of line will basically cause a change in a magnetic flux. So this change in magnetic flux will basically cause a production of an electromotive force in this closed circuit wire or closed circuit coil. So whenever there is an electromagnetic electromotive force in this closed circuit coil, there will be a production of an electric current in this coil. And this current is known as an induced current. So we know that the circuit is closed circuit. And the current has a specific path to flow through this circuit. So in this way, current will basically flow through this circuit and will go toward the galvanometer, and galvanometer will detect the induced current. So in a simple word, keep in mind that electromotive force do not require the production of an induced electromotive force do not require circuitry requirements. However, for current, the the circuit must be a closed circuit, and closed circuit basically give a path for a current to flow. Now, student, please keep in mind that there are some key points you need to remember. The motion of magnet toward or away from the conducting coil basically cause a change in a magnetic flux, which causes an induced EMF. But if the motion is the magnet is in a stationary position, or it is just placed, then in such situation there will be no production of induced EMF if the coil is also in a stationary state. However, if in this case, if the magnet is stationary, in this case, if the coil move forward toward the magnet or move away from the magnet, then in such situation there will be a generation of an electromotive force in a coil, which will basically induce an electric current. So for the production of induced EMF, the relative motion of the magnet or a coil is important, because the relative motion of both basically cause a change in a magnetic flux, and change in magnetic flux is basically responsible for the generation of an electromotive force. Now, a key point to notice here is that if the velocity of a moving magnet is 4 meter per second and 4 meter per second, and similarly if the velocity of conducting coil is also 4 meter per second, sorry to be clean, it is also 4 meter per second. So this means that speed of both conducting coil, suppose the direction is thisward, like they are moving toward the forward direction, so the both are moving basically with a velocity of 4 meter per second, and so this means that since the velocity of both is same, this means that there is a no change in a magnetic flux. In such situation, the magnetic the current induced by a wire will be basically the electromotive force induced in a wire will be zero, and the current produced in a wire will also be zero. So, students, please keep in mind that relative motion can generate an electromotive force, but for relative motion we need to have a change in a magnetic field of line, and as well as change in a magnetic flux. The change in a magnetic flux is only possible whenever velocity of one is different. Suppose that velocity of wire is 2 meter per second and velocity of other is different. Suppose velocity of magnet is 4 meter per second. So difference in velocity basically will cause a difference in a magnetic field of line, and in this way electromotive force may possibly be generated in a coil. So this means that whenever there is a change in a relative motion, V relative, there will be a production of an induced EMF in a coil, and this induced EMF will basically generate an induced current. The flow of the current will be determined on the basis of the path. So for current to flow, a closed path is required, which will basically cause a generation of a current in a coil, or generation of an induced current in a circuit. Another important point to notice here is that the direction of induced current will depend on the direction of north or south pole. So they basically will play a vital role in the direction whether the current will flow clockwise or anti-clockwise. Usually in when a north pole come toward the current, the flow of the current is basically is anti-clockwise. But this, in a simple word, the direction of current will basically depend on the direction of the magnetic poles. Okay, so for south pole the direction of current will be different than the north pole. So this is all about the Faraday first law of electromagnetic induction. Whenever there is a change in a magnetic flux, there will be a production of electromotive force. However, induced current will be produced or will flow in a conductor when it has a closed path for a current to flow through it. Now, student, let us discuss Faraday's second law of electromagnetic induction. Faraday's second law of electromagnetic induction. Faraday's second law of electromagnetic induction states that the magnitude of induced EMF, the magnitude of induced EMF is directly proportional let me write it in a statement, is directly proportional to the rate of change in the magnetic flux. This means that whenever there is a change in a flux, there will be a production of an induced EMF. And the greater is the change in a magnetic flux, greater will be the production or greater will be the magnitude of induced EMF. So this means that an induced EMF is directly proportional to the rate of change of magnetic flux. Greater will be the change in magnetic flux, greater will be the amount of magnitude of induced EMF. So in the form of magnitude, we can write this like this as EMF is equal to we can write modulus into rate of a change of rate of a change of a magnetic flux. Let me clean it and write a magnetic flux phi b divided by t. The term the sample, this is basically as a representation of a modulus which basically it's represent a magnitude of a change of a magnetic flux. So now dear student, a change in electromotive force may take place at a particular instant. Such type of change in electromotive force is known as instantaneous electromotive force, and it can be represented as rate of a change of a magnetic flux at a particular instant of a time. Instantaneous, you can write instantaneous. So now another important point to notice here is that with a second law, Faraday's second law of electromagnetic induction, a sign negative minus is used with change of a rate of a change of a flux. The sign negative is basically tell us the direction of an electromotive force with respect to the change in with respect to the magnetic flux B with magnetic flux B. This means that the direction of electromotive force will be opposite to the electro to the change in a flux. So we will discuss this the negative sign. There is a law which is used to explain the negative flux, and that law is known as Lenz's law. So we will explain Lenz's law in our lecture about Lenz's law. So this negative EMF, induced EMF, will be equal to change in a magnetic flux. And since you know that, dear student, according to Ohm law, basically now we can also find an induced current. How we can find an induced current? As you know that, dear student, according to Ohm law, voltage is equal to I into R. So I is equal to current is equal to basically voltage divided by resistance, voltage divided by R. So EMF is basically, it is also represent a voltage. This means that if we can basically write a voltage as an induced EMF. So then induced current will become, as you know that voltage is basically EMF, voltage is EMF, and EMF is equal to rate of a change of a flux. So we can write this like the equation voltage as like this, and divided by a resistance in a wire. So in this way basically we can calculate a current, induced current in a wire, by including value of a induced EMF, which is basically a rate of a change of a flux and a resistance of a. So if I conclude the Faraday's second law of electromagnetic induction, second law of electromagnetic induction states that the magnitude of induced EMF is directly proportional to rate of a change of a magnetic flux. The greater is a rate of a change of a magnetic flux, greater will be induced EMF. And whenever there is a greater amount of induced EMF, the value of current will basically change, or it will depend on the induced EMF. So now we can write that the Faraday's second law in an equation form, that induced EMF is equal to rate of a change of a flux. However, negative sign is used for a rate of a change with rate of a change of flux. The reason for using a negative sign is that the direction of induced EMF is always opposite to the rate of a change of flux, which is basically determined by a Lenz's law. So now we have an induced EMF. Now, important point to note here is that if we want to know the current induced by in a coil, as we know the value of induced EMF, then for knowing the current in a coil, in a wire or a coil, we need to have a closed circuit. And whenever there is a closed circuit, so then in that case we know that voltage according to Ohm law is equal to I into R. It is equal to current into resistance. Then current is equal to voltage divided by resistance. Voltage is an induced EMF. An induced EMF is basically the rate of change of flux. So we will include the value of induced EMF here, which is basically a rate of change of flux, and multiply by resistance. So in this way, we can basically calculate an induced current in a circuit. So this is all about Faraday law of electromagnetic induction. So thank you for watching this lecture.